Oh, yes. Thank you.
Go ahead.
Okay. Welcome everyone to HO Colloquium today by Christoph Keller. It is my great pleasure to introduce Christoph Keller. Christoph Keller's research expertise spans exoplanets, solar and stellar magnetic fields, planetary atmospheres, and innovative optical instruments for astronomy, remote sensing, and biomedical imaging. He authored or co-authored over 450 publications and received the Friedrich Wilhelm Bessel Award for Outstanding Astrophysics Research. Christoph's career includes a decade at the National Solar Observatory in Tucson, where he led the iconic Magnetosphere Solar Telescope. He then joined Utrecht University, becoming its Astronomical Institute director. He served on oversight and visiting committees and chaired the board of the Isaac Newton Group of Telescopes on the Canary Islands. After 10 years at Leiden University, he joined Lowell Observatory as Director of Science in 2022 and returned to NSO as Director in May 2024, focusing on fostering a conducive environment for scientific research. Today, Christoph will be speaking on Invert Everything, Everywhere, All at Once. Christoph.
Thank you, Masumi. It's a pleasure to be here, particularly in an environment where, inversions basically came from in solar physics. And so, and probably not just preaching to the choir, but you know a lot more than I do. So here is some crazy idea that I have been playing around with, and I'm trying to explain it in different ways. Sound good? So let me go ahead here and actually explain to it why this title is not just kind of a reference to a movie, but it is fundamentally important that we do it this way. So let's jump right in. Inversions, well, they start with observations, right? And then you assume you have some physics in the atmosphere. Almost all inversions assume that you have hydrostatic equilibrium, particularly in the vertical direction. Sometimes you have the divergence of the magnetic field is zero, as it should be, but that's probably only a few codes that do this by now. So it's a very limited set of physics that goes into these model atmospheres that you create out of that. So you make a model of the solar atmosphere. Typically, it's just along one line of sight, right? So it's basically just in the Z direction. And you have some free parameters in there. And typically, they're like the temperature at 4 different places in that height, and then you interpolate between it. Temperature is in there, and the magnetic field is in there. And that's what I typically call this U vector. That's just all the physical quantities in the atmosphere. And here is a function of height, Z, and then the free parameters are just the vector theta. Different codes use different approximations. Most of them actually do not even work in Z, not in a geometric height, but they work in an optical depth. So it's a variety of ways. Then you take this atmosphere model, you run it through some radiative transfer calculations, and you create what I call here synthetic observations. Right, so this is what this model would create if it would be a solar atmosphere. And then you simply take the observations, you take the synthetic observations, you calculate something like the sum of the differences squared. And going towards machine learning, this is often called a loss. Right? It's just the RMS difference or the variance between the observations and the model. And so then you take that loss and send it to an optimizer. There can be some complicated thing, there can be a simple thing, and it will simply update the free parameters to, in the end, make this loss as small as possible. So you have the new model parameters, the free parameters, and you run this loop over and over again until your model explains the observations as about as good as it can. So this is your classical inversion scheme. That's one way to explain what we see on the sun. The other one is what Matthias is doing. You go from pure physics, you start with some random field, let it settle, and then you suddenly have a beautiful movie of the solar surface. Having come back into solar physics not too long ago, it's absolutely amazing to me. By now, I can't tell the difference anymore between the simulations and reality. But if I want to have a certain observation explained by a simulation, then it gets very difficult. Right? You can do statistical comparisons and so on, but actually explaining exactly what you see in an observation doesn't work so well. So let me show you.
Can I just ask a question?
Yes, absolutely.
Why are you updating theta? I mean, that's like it shouldn't be updating you, optimizing you.
Well, theta are the free parameters, right?
You're not optimizing for the U, all the
No, the U is not optimized at all. Right? That's just the U is like some type of physics that calculates that, like you assume horizontal pressure equilibrium, so gas pressure plus magnetic field squared is the outside pressure, something like that. But what you do is you change these free parameters. These may be the temperature at a certain height, and then to get U, you have to interpolate through those points again. But you're up to something, and you'll see what we do. We'll turn around one of these arrows. So I thought I'd show a little bit a comparison. So on the one hand, we have this classical inversion that I just showed. On the other hand, you have the numerical simulations like Muram. And then let's see what we would like out of this everything, everywhere, all at once, right? What is that we would like? And of course, we'd like to combine the advantages and get rid of the disadvantages of the different approaches. So when you look at the dimension of the problem that is being addressed, for classical inversion, it simply is, in most cases, it's one line of sight that you invert. And then you go to the next line of sight. So basically, pixel by pixel, you invert, and they don't really know very much about each other. Sometimes almost nothing. Sometimes they're corrected so that the divergence of B is zero, but that's kind of it. Numerical simulations are completely four-dimensional, 3 space, 1 time. That's, of course, what we'd like to have. In terms of the physics, inversions, the physics of the radiative transfer is normally extremely good. There's great details, non-LT and so on is in there. But when it comes to the model of the atmosphere, like obeying the MHD equations, then that tends to be pretty bad to non-existent. So what we would like, of course, is, yeah, all the physics should be right. Now, when you come to data assimilation, so the question of trying to actually explain actual observations, how do you make the model fit the observations? Then, of course, the classical inversion is excellent because that's exactly what it optimizes for. The numerical simulations, it's not trivial to put in the observations. It's a little easier if you look at coronal magnetic fields, where you just have a boundary condition that drives everything. But for something like in the photosphere, that's significantly more challenging. And of course, what we would like, we want to have excellent assimilation of the data. Speed, inversions overarchingly are very fast. Of course, you can make it so complicated with non-LTE and non-equilibrium, and I don't know what, that it can get fairly cumbersome too, but overarchingly it's pretty fast. Numerical simulations are not as fast. I know Matthias has made great progress, so we can have a go at it who is faster. But what we want is speed that's good enough, right? Ideally, we'd even be able to choose how fast do we want to trade off. The last one is an interesting, that's the accuracy. Right, the accuracy of inversions is typically pretty high, in the sense that the radiative transfer is done very well. So if you only look at how well the model, which may not physically be that good, but how that translates to the observation, that's normally done incredibly well. calculations are done at least 32-bit, if not 64-bit. Tends to be very high accuracy. Same thing with the numerical simulations. They tend to be very highly accurate. For us, it would be just good enough. If the data are not particularly good, why should I worry about having all the physics exactly right? Right? So you'd like to trade off the accuracy in different parts of your system. So that's kind of what we're shooting for. So what we would like to do is we would like to throw in all the data we can find. Let's say we observe a flare. We'd like to throw in everything we can, SDO, ground-based, whatever, from any observatory. Just put it into the thing and get it inverted. So that's kind of the hope in the end. There's some issues with that. If you look at classical inversions, they need the data at the same place all at the same time. Because they invert and create the model, typically it's actually hydrostatic. Sometimes they include velocities or vertical velocities, and at least it's kind of stationary. But time dependence is typically never a part of inversions. So when you look at where you have the data, well, EUV gives you nice, big, full sun image. Every so often, maybe once in a while, there's a data glitch. If you have something like a scanning spectropolarimeter like this, well, that takes the scan and scans across with a slit the surface. So if you're in one part, you scan here, but to go to another part in space, you actually have to wait until the slit is over there. Right? And in the meantime, there is time evolution. And then you have clouds sometimes, you get no visible data. And then you have something like a filter imager, but that's a small field that mosaics. Well, they will take snapshots of different parts of the solar atmosphere at different times. So if you now try to find a place where all the observations occur simultaneously, it gets really hard. Now, of course, you have a little wiggle room, how much changes within a few seconds. Right? But when you're a few minutes apart, then you already have to ask yourself, is this really still okay to do? So really, to deal with data like this here, and of course, this is all made up as an academic example, but to do all of this, we really would need to invert everything at the same time. Right? So we know that sometimes we have this data, other times we have other data in different places. So this is a little bit where this idea comes from, that we have to really invert everything at the same time. There's another reason that I'll get in later. The other thing is we really would like to put in all the physics, right? I mean, we know these laws of physics, so why shouldn't we use them to our advantage? And most inversion codes these days, they can do a few of them. The radiative transfer tends to be done very well. Other things are not like that at all. But the continuity equation for mass flows typically completely ignored. So what else do we want? Right? Here's my wish list. You all know that no instrument is perfect, even if it's in space. It has a point spread function. So we should include that in our modeling. We shouldn't assume that this is a real solar data, but this is the solar data kind of smeared out a little bit. I understand, I think Jaime has a code that can include that now. There are other things. We'd like to do this anywhere on the sun. At least in the past, inversions had a lot of issues if you didn't look at the center of the sun. I really don't know how it is now, but in any case, I want to do this anywhere. Depending on the problem, I'd like to have some, flexibility and resolution. And really, if I have a good model, why not be able to let it just keep running without the data? And so we can extrapolate in time. So for space weather, we observe a sunspot or, 12 hours or whatever. We put it in this inversion and creates a perfect physical model for us, and we just keep it running. See what happens. Is there a flare going off or not? We also would like these models to not be extremely huge, but then it gets troublesome. Once you get into the terabytes, then it just gets cumbersome. We talked a little bit about accuracies. We'd like to be able to tune the accuracy to kind of be compatible with the noise and the data. And then really my pet peeve is that I don't want to have to solve any physics equations. I just want to throw in the equation. Well, it sounds a little crazy, but I think we can actually do a good part of that. That's because I'm lazy and I don't want to learn how to do that. So laziness is always a good driver for thinking in different ways. I have to do a little bit detour here about neural networks, just for those of you who maybe have not looked into that much. The first thing is a neural network can approximate any function in any n-dimensional space with arbitrary accuracy. We can prove this mathematically. Yes, the neural network may have to get very, very big to do that, what you want it to, but it can. So think of neural networks being able to represent any arbitrary function to any arbitrary accuracy. Neural networks are here a very simple one, a multi-level perceptron. You see this at the bottom right here. What you typically have are something like input nodes. This is where you send in your signal that you have. And then you connect to something like a hidden layer, where every hidden layer gets information from every input node. And at each of these nodes, you basically calculate a weighted sum of the inputs. You add what's called a bias or an offset, and then you run a nonlinear function over that. Typically, for what I'm doing, the hyperbolic tangent. The reason for the hyperbolic tangent is that it's limited to ±1, which makes it inherently your values will not go out of crazy bounds. And you can take arbitrary orders of derivatives. It's not that at some point the derivative disappears or does something crazy. So that's why for the type of work I do, the hyperbolic tangent is a good one to choose. And then you can have more layers here, where again, you take the output from each node before, you do a weighted sum, you add a bias, you take an nonlinear function of it. And then at some point you declare you have an output, that's the last node, or you may or may not do the same thing, and that's where your output is. So the important thing here is this is all very easy mathematically, and it's all analytical, right? There's nothing fancy. You can write down everything analytically, and that's important in the end. So just as an example, and it's the question, can a neural network approximate the solution of one of these Bifrost simulations? Well, it's an MHD simulation that I've been using. And what you see on the top row are all the physical parameters at a certain height for the Bifrost simulation. And then at the bottom, I trained the neural network to replicate that. And it's pretty darn good. The new thing here, for those who have seen the talk before, it also includes now the magnetic field. And you can see even relatively fast switches here between polarities. It's represented pretty darn well. It's maybe a little fuzzier, a little smoother, but it works just fine. Now, the funny thing is that the Bifrost simulation, that's about 10 to the 8 parameters that are in there, while the neural network that does this is about 2 times 10 to the 5. So it's about a factor of 500 compression. And that will depend, of course, a little bit on the simulations that you try to do, but inherently the neural network does like an optimum style of compression. It's a highly compressed representation of this time sequence. So yeah, neural network is fine to approximate something like this.
Only is time.
20 is time, yeah, 20 time steps, 50 seconds each. So that's just an example, so it's actually it doesn't take that much memory to store that information. And there are advantages that you can work with. So now we get to what's called the physics-informed neural networks. And a physics-informed neural network you can think of as a different way to solve partial differential equations. This was introduced by George Karniadakis and his PhD students at Brown University. It has completely taken off by now. I think George is now about the most highly cited applied mathematician in the world. So the idea is the following, that when you have a differential equation, let's say du over dt is equal to some differential operator on u, fairly, you can imagine any kind of partial differential equation like that. You simply write this as a constraint, right? So you rewrite it such that yada 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 equals 0, and that's what you put into here. And instead of trying to solve this with your standard Runge-Kutta or some other time-stepping algorithm, you simply say, okay, this is the constraint that I have to fulfill. Constraint-based solving of differential equations is nothing new, but the advantages in AI have enabled this to really work fast. So what you do is you say, well, this differential equation has a solution u, let's say space and time. And what we're saying here is, well, we don't know what that solution is, but we know that the neural network can approximate it, because that's always true. So we say, okay, let this u be represented by a neural network. And then we train this neural network to fulfill this constraint. And that means the neural network gets informed by the physics that we expressed here. What is really nice about this is if you have observations and you want to have, solutions to your model atmosphere, your radiative transfer, you can do exactly the same. You remember before we had this loss between observations and the synthetic observations? We can plot this in here too. It fits. So basically what you do is you reformulate solutions to the physics problem as a constraint. And that matches all what the machine learning and AI has been doing. The big step forward in AI was that realizing that if you have these analytical neural networks, and they're all analytical, you can calculate any gradients, any derivatives with respect to these parameters extremely fast. So let's say I have 1 billion parameters. Typically in the past, when we did inversions with something like Levenberg-Marquardt or whatever, you numerically said, okay, I'm here. I'm now numerically calculating the derivative. And for every free parameter, I add a little bit, I subtract a little bit, I calculate numerically the derivative. So the time it would take you was like 3 times a function call for any dimension. Right, so for any free parameter. So it completely explodes when you have a lot of free parameters. With the analytical system, there's something called automatic differentiation, which is basically just a clever application of the chain law for derivatives. And that means that you can calculate the derivatives of every single parameter within the time it takes to do a few function calls. So instead of doing 3 billion calculations for a 1 billion parameter problem, you're talking about doing a few calculations. Right? That is huge. And that's what inherently makes all this AI working, that you can calculate the derivatives so quickly. And of course, we have the software and the hardware, right? I mean, I have an M3 Max in this laptop. It's like 35 teraflops on the GPU, 64 gigabytes of RAM. I can do the most crazy things. I run a 20 billion large language model on there. No problem at all, right? And that's the beauty, that everything is here. You have all the software. It's all free, available. You can really do that these days. So that's where the physics-informed neural networks come from. Now, let me give you an example just to have a little bit of an idea. I'm using this damped harmonic oscillator here as a problem. Very simple differential equation. You might have some boundary conditions. We know how to solve this, right? There's analytical solutions. So I have here the exact solution here shown, and then a numerical solution with time-stepping algorithm. No problem. Does it just fine. So now, if we want to do a network, well, here's a no physics network. If I just try to train a neural network to kind of tell me where these different points here, how they might be connected, this is what I get out. The neural network only knows about these few points. It has no clue what's happening out here later in time, right? So it's about as good as it can do. Now, this one has only trained on the data itself. If I now also train it on the physics, you get this green line, which almost perfectly matches the exact solution. And so instead of just fitting the data here and saying that the synthetic output has to match the data, I'm actually also demanding that the differential equation be obeyed. And because now it knows the physics, it interpolates correctly in here. Look at how well it gets the minimum and maxima here, despite the fact that there are no measurements there. It can do that because of the physics. And the same thing is the extrapolation. This thing can actually tell you how this evolves. Because now it knows it's a harmonic oscillator. It cannot just go and do something crazy. It has to keep oscillating. It has to keep the damping. Right, so that's the idea behind the physics-informed neural network. It's simply a neural network where you tell it you also have to obey the physics. So if we now try to apply this to inversions, this is what I showed you before, the classical inversion. And I'm going to show you how we manipulate this a little bit. We're going to change this a little bit. And we're adding a few things. So I'm assuming this is the arrow that turned that you were wondering about. So now we say, well, the solar atmosphere, I'm not worrying about the physics at all. I'm just saying I make a neural network of the solar atmosphere. The input is X, Y, Z, and T, and the output are all the physical parameters. And so, of course, I can take that and make synthetic observations out of it again. No problem at all. And I can calculate the loss. I can send this back to an optimizer and so on like before. But the additional part is now that we also send this output here to the physics. And we say, okay, neural network, you have to obey the physics. So we take all these partial differential equations and we say, you have to obey these two. And this is actually pretty darn easy because you see we have in here derivatives. Once a neural network calculating the derivative with respect to time or space is trivial. It's literally for all the hydrodynamics that I'm enforcing, it's like 5 lines of code to get all the derivatives. No problem at all. And so then in addition to this observing loss that we had before, we now have also what we call the physics loss. So this is the continuity equation here, for example, reformulated as a constraint, and we say you also have to minimize that. So it's simply a minimization problem, which has made it a little bit more complicated. We're adding the loss of the physics and the observations, send that to the optimizer, and update the neural network model. So that's the basic idea behind this, how to do this. The other thing you see in here is, of course, that now I'm using all the coordinates, right? I don't see Z because typically I have a line of sight along which we integrate, but I'm actually including everything. There is no, this is really everything everywhere all at once. This model here models everything at once and gets trained on everything all at the same time. So this is the idea. I'll go back again and just show you It's really not very much that changes. The big thing is this arrow that we turn around, or our model now that before had physics in it, we make a neural network. We don't include the physics there. So that's the idea behind this. Now comes the crazy thing, right? So I was thinking about what is an inversion problem that a standard inversion cannot deal with. And that's simply if I have a sequence of continuum images of the solar surface, I want to get out temperature, density, pressure, velocities, everything. I'm not worrying about magnetic fields right now. And that's no existing inversion approach can do that. Just having the continuum intensity is not enough. And so here's what I did. I made a neural network that takes X, Y, Z, and T and spits out the velocity in 3 dimensions, the logarithm of the density and the logarithm of the temperature. Logarithms are nice because they compress the scale, particularly when it comes to things like density that drops off exponentially with height. Neural networks like to have things between -1 and 1. They like to have, in that range, that's where they're most comfortable. So you have to kind of accommodate that, you scale inputs and outputs. Another nice thing here is that I'm spitting out the temperature, which is not necessarily how you would do this with a model. In many models, you use something like an energy equation, and you work with let's say, an internal energy per unit mass. Here I can just say, okay, my network spits out temperature. And that makes something like calculating the equation of state or calculating ionizations tends to make that a little easier. So the network is actually shown graphically here. There's 44,000 parameters, so not particularly big. And then the physics equations, that's simply your standard continuity. So mass is preserved, momentum conservation, energy conservation, and then an equation of state. Equation of state is very simple, it only assumes that hydrogen ionizes, nothing else. Then, as I say, quantities that may change rapidly with height, like density or pressure, we take the logarithm. And then things like the internal energy or radiative losses or opacities, that's always with respect to unit mass. So again, these quantities don't change that rapidly with height. There's nothing new. It's just the equations start to look a little bit differently when you work with the logarithm of the density, but really not much. You reformulate it so it's equal to 0, put this in as a constraint. Now, there are some things that you have to worry about here. And sometimes the training may go to something like what I call a trivial solution. And you have to keep it away from a trivial solution. So the example here for the continuity equation is, for those of you who are into this, you know that the density change with time is very small. That's why the anelastic approximation, where you set this whole term to 0, is actually pretty good in the solar photosphere. So we know this term is pretty small. If you look at the rest of the term, the easiest way for me to make this term go almost completely away is to set the velocity to 0. So the network naturally would say, like, oh, I can easily solve this. I just set the velocity to 0. And that's not what you want. Now, the term in brackets here, we know this should be 0. So I can multiply this constraint with anything I want. So in this case, for example, I divide by the variance of the vertical velocity. If it now tries to make the velocity 0, this term starts to explode. Because the variance goes to 0. So this lost term here, this explodes. And this fixes it. There are other equations that you don't have to worry about that. Nothing happens. So yeah, there is a little bit playing around with things. So does it work? At the bottom, you see the Bifrost simulation. over about, I don't know, what is it, a few minutes. You see that evolve, you see the vertical, the horizontal velocities. On the left is the image. So the Bifrost image here on the bottom left, that's what I used as input for my physics-informed neural network. And then it spit out all the atmospheric quantities. That's pretty darn good, right? So only using intensity images as a function of time, it gives you back most of your atmospheric parameters. It's not perfect. Horizontal velocities are really difficult to get out correctly. And that's mostly because if you look at the equations, most of the equations you can actually add a constant horizontal velocity and it doesn't change anything. Because in many cases, it's the derivative of the horizontal velocity that comes in. So it's like an offset that you can add. So there's some, some things that are not trivial to do. But I felt very encouraged by this, really an inversion problem that a regular code cannot deal with at all. So, and then you can look at slices, vertical slices here. You see that, well, whenever you're kind of in the middle here, where most of the light in the continuum comes from, it's pretty good. When you go above, well, not so sure how good that is, largely because I don't have any of the physics in there. When you go below, well, my code, it makes the simplest assumption, matter just keeps going down, right? If you look at the Bifrost here and vertical velocity, there's a lot of funny thing happening below the surface that the code doesn't capture. Now, whether that's inherent, because there's no information about that, sometimes I'm wondering whether I see some effects from the lower boundary in the Bifrost simulations. I'm not sure. But for those who are interested in the, do I see the inverse granulation? If you look up here in my inversion here, you actually see that it's hotter above the intergranular lanes. So I think I kind of get that, despite the fact there are no observations in there. So how about real data? One of these is Hinode, the other one is the PIN result. Those of you who have stared at enough Hinode data can probably tell the difference. The real data is on the left, the inversion is on the right. The beauty, of course, is now if we look at the inversion, we can again get back things like the vertical velocity out of these image sequences. You also get the temperature here. You can see there's a slight tilt. Still working on that the solar surface actually has to be kind of horizontal. There's still some issues there that sometimes just wants to tilt the whole thing. So this is really initial stages of trying something different. Advantages of the approach is also, this went too fast. Okay, so here's one of these beautiful decast images showing these small scale magnetic elements. Well, really would like to focus on these, right? So if we have to do anything like point by point or have to look at the physics in different places, we actually want to look at these things. And again, with these neural networks, that's trivial. The neural network exists everywhere, right? It automatically interpolates, it automatically extrapolates. If I need to do something in space or time, it's trivial to do. So some of the things that are not working yet. If my physics is all correct, it should be able to interpolate, right? So what I did is I took the Bifrost data. Actually, I'm not sure whether it's Bifrost or Hinode. Actually, it doesn't matter at all. I took images at certain time intervals and then recreated images in between. One just taking a linear interpolation of images, which is the most basic image interpolation you can do. And then I also ran my physics-informed neural network. If the physics-informed neural network here in blue is correct, it should represent images incredibly well. It should do much better than a linear instrument with the images themselves. Well, it kind of doesn't. It's about the same. Sometimes it's better, sometimes it's worse. So something is not right yet. It's probably because the time, if you see between images here, is more than 100 seconds. That's probably a lot of time where I would need to enforce the physics much more frequently. Something to work on. The other one is extrapolation. So I took the Hinode data, I trained for half the sequence and then stopped training on the images at all and just let it evolve. And I can see, for maybe 20, 30 seconds, it does okay, but then it all goes poof. I'm not sure I understand why this is like that. It makes this very bright thing here. So the total energy output is still okay, but we all know it's completely unrealistic. So, something for the future. So what's next? Obviously should add magnetic fields. Everybody wants that. But we all know magnetic fields are a pain in the butt. So then we want to add observations. We would like to have line of sight velocity. We'd like to have magnetograms and so on. Would like to do this over larger areas. Maybe we can do this locally, something like, a mesh refinement. I'm not sure. Would like to do inclined lines of sight so I can really invert factually. Would love to do that. And then, optimizer is always an issue in these things. Try to do that better. So let me just show you two things here. One is 4 times larger area. This is a network with about 500,000 free parameters. It goes a lot slower. The other thing is also, if you look at this, these granules are a little wibbly wobbly on the inside, a lot of variation. If you look at here's the horizontal velocity. I'm not sure if this comes through, but if you look at my monitor, there's some kind of, jittery, noisy thing on. I think you see it most clearly in the cuts where you see the vertical here. So Z is in the vertical here. And you see like the neural network is actually fairly noisy there. It has these small scale structures. When I do it on my smaller area, the neural network output is always smoother, which is fine. I can work with that. Once I increase the field of view by a factor of 4 and increase the number of free parameters, it gets this kind of jittery. I let it run over a weekend to optimize. It didn't help. So there are inherent things that have to do something with like the dynamic scale that a neural network can represent. Not clear to me. This is applied math at a level that goes way beyond me.
So the bottom and that narrow strip is the cut from the top?
Yep, that's a cut through. So this goes from, minus 800 to about plus 500 kilometers. And it's just, it gets noisy. It gets this like filamentary structure in here that's not real. It could be something like Gibbs phenomena where it's ringing. It's not clear to me when you do a neural network that does this big a thing. I mean, does the granule at the bottom right, really worry about what the granule is doing on the top left? At some point, the interactions over larger scales, just in hydrodynamics, must become less. So there must be kind of a way to deal with that. There are ways you could do this with like a hierarchy of networks where you have one that looks at the large scale, then smaller, more local ones. I don't want to deal with that index accounting. I'm trying to see whether there's a clever way. I'm thinking about things like wavelet positioning coding, things like that, where there's some local aspect that you can control how far out it goes. Again, when you look at the literature, there are tens of thousands of papers. They all deal with some, like the Burger's equation in 2 dimensions. It's all the same thing, and they do maybe a factor of 2 better than the previous paper. But rarely ever does anybody worry about real stuff. So there's a lot of open things here. The other thing I wanted to show was, and that's new too, is I need to include more data. So one example is line of sight velocity, right? If I'm just dealing with hydrodynamics, it would be nice to not just have the images, but include the line of sight. When you have a spectral profile, one of the easy things to calculate is something like the center of gravity. You just take the absorption line, you do continuum minus the absorption line, so you get something like a Gaussian, and you simply calculate the center of gravity of that in wavelength, transform that into velocity. That works pretty well. So you see down here, this is the center of gravity velocity, calculated with full LT radiative transfer all correctly. And so the question is now, how could I include this in my neural network? And one idea, I think I talked about that before, but never did it, was that I expressed the line of sight as like an integral of a kernel that depends on all kind of atmospheric parameters and integrate with respect to the continuum optical depth. Now we can talk about how good this is. I think for LTE, it's probably not too bad. We'll have to see. So I did this for the center of gravity velocity. I calculated the kernel, and lazy as I am, if I need to calculate something, I just train a neural network to do it, right? So what you see here on the bottom right is the contribution function to this center of gravity velocity as a function of continuum optical depth. And this was trained by training a neural network on simulated data. And that looks about right. It should, in the wings of the line, you go fairly deep for the Doppler signal. Higher up, you get less. It should be steeper on the right than it is on the left, as about right, you know. So, and then if I use that to calculate what the velocity is, I actually get a good match to within 100 meters per second. I want to do the same thing with magnetic fields using, again, center of gravity, I plus V, I minus V, see where I get with that. So those are the things that are in the works. Let me give you a summary. Sorry, I've been running over a little bit. So really, this kind of an inversion, it's a space-time continuum for those in sci-fi. This is the real thing, right? Any time, any space, the neural network can calculate what it is. And so we look at everything, anywhere, all the time. So if we have observations at different times, it's no problem. The model will interpolate. If I have an X-ray image at one time slot, I have a ground-based magnetogram 2 minutes later. That's fine, because the network can deal with it, all of that. So, and because these neural networks, if I tune one parameter a little bit, it will affect the whole thing over the whole volume in time, right? So actually, when I tune these parameters, it really does influence everything. Now, whether that's a good thing or a bad thing, we can talk about. It's probably a little bit both. And if you're interested in the details of just the hydrodynamic thing, here is the reference to the APJ paper that I wrote up. So thank you.
Thank you. So questions from the room and from online? Robert.
So I was wondering for like when you keep on running the simulation, right, and like take out like the constraints from the intensity observations. Does it make sense that the simulation like drifts away because you don't have any more like boundary conditions that can constrain the simulation there? Is it like basically that the network still satisfies the equations, but since there's no boundary condition, it just pushes it towards like a very trivial solution where it can just
Most likely, yeah.
And so like related to this, what are you using? Like it's clear when you use the intensity observations that you have it basically constrained through the volume by
right.
Also like on the sides. But do you impose any other conditions on the remaining boundaries, also like below the?
So here's the additional constraints that I apply that I found to be very useful for this. One is the total energy flux. Doesn't matter in which form, it should always be about, let's say you're based on the watts per second per square meter that comes out of the surface. Right, so I calculate the total energy flux and then keep that constant. That helps greatly to also kind of keep driving the convection. The other thing I say is that there's no vertical mass flux. Right, there's no net. If I add all the mass flux over any horizontal plane, it should be zero. Now, this gets a little bit tricky because Bifrost, like most numerical models, they actually do not have that. They tend to go up and down. And that's a pain of its own when you compare to that, because sometimes, I have my model, which I enforce to basically not oscillate in any form or fashion. And then you compare to something that moves around.
You can subtract the box mode kind of when you do the comparison.
That's what I have done, yeah.
Okay.
Yeah. And then what I do is I prescribe the mean density and temperature profiles. And the reason for that is that initially the neural network has not the faintest idea. It doesn't know about stratification or anything like that. And this applies very early on, so it's just like, okay, no, the pressure doesn't go down as you go into the atmosphere. This is just wrong. Gives it a huge error signal and makes sure that very quickly the network has some kind of reasonableness. We have the images that we talked about, and I do leave out acoustic and kinetic energy flows, and there's some approximations, but the main thing is that there's no net mass flux and the energy flux has to be constrained, but there's nothing on the sides. For example, I talked about this tilted atmosphere. It can kind of like run out of the box. And it starts to have a consistent horizontal velocity in one direction. And it kind of drains out of the edge of the box. So there are probably things that I need to say, okay, there is maybe no net horizontal mass flux or something like that. It's beautiful not having boundary conditions. But I think particularly when you extrapolate, you probably hit the limits of that.
Very nice.
At least when you compare it to the numerical simulations, you can likely also assume periodic boundary conditions in your network, which would be likely the easiest to implement.
To work with simulations, yeah, absolutely.
At least that would be a way to test if it's a boundary condition. So
That's true. Yeah.
A related question, do these additional constraints contribute to loss?
Yes, absolutely. So there are like 12 loss terms or so. I think Rebecca.
Mike. Oh, okay. Rebecca, then Mike.
I think you just alluded to it, and I was trying to understand. You say that there are no constraints on the horizontal velocities is what made that continue tilt when you fitted the, because I was not
Totally sure.
systematic in the observations that could have led to that.
I
mean, we know it has changes in, for instance, continuum intensity as the slope progresses across the distance.
Well, this is from the imagers, so I think it's okay. But a lot of this is like you see it and you have a gut feeling for what it could be. It's like, and I have to say, I don't have that much time.
No.
So it's like progress is very slow.
I don't know how to do any of this, but it reminded me of something that Robert showed me the other day, where you use these new masks to compensate for systematics in the observations, but you let the neural network kind of fill in what was systematics versus what was the real. So I was wondering whether something like that could be an approach to.
Could be. I think where this approach would be beautiful is to determine the point spread function.
Yeah.
Right? Where it does the image reconstruction at the same time. Now that's crazy.
It's not.
Mike.
He's doing it.
Cool.
I'm curious about the computational costs of training the network versus the cost of running the simulation, and then how well I assume once you train it, you've got a neural network that you can save and you can run on any data set.
Nope.
Yeah.
This is not AI. So this network can only represent these observations. There's no, maybe in the far future, we get to something like neural operators, where we can do some of that, but we'll have to see.
Okay. But till then, I'll just fall back to my earlier question. What's the computational cost? What level of
So
research?
on my old laptop, which was a Apple M1 Pro, it was faster than the evolution of the sun. So if I took a 30-minute time sequence from Ionosphere, I could do this in less than that time on my laptop. With a new laptop, it's a few minutes. Another reason why I'm not liking with the going to 4 times bigger field, that gets a lot slower. So I decided I'd go back to do the developments, things like that on a small field. So most of the things I do go within a few minutes.
So your training set is a set of Hinode or Bifrost images.
Yep.
Of the size you showed.
Yep.
Over how long?
Yeah, it's
How many
30
images?
minutes.
So a couple hundred images.
No, I only use an image every, 30 to 60 seconds.
It's continuum intensity, what you show it.
Yep.
Yeah.
If you look at the Hinode data, the neural network that captures the whole time evolution in 3D is less in terms of kilobytes than the Hinode data set that I'm using.
Yeah, I'm surprised it's converging on that small a training set though.
Well, it's
Fairly large network you showed there, fully connected.
well, 40,000 parameters is
Yeah.
not that much compared to all the data. And the physics constraints, right? The physics constraints are very hard. That's why I can do this, right? I mean, there's very little information that I actually put in, and the constraints come largely from the physics.
And
So if you look in the literature, they have now observations of like flows and things like that, where it's just in a few spots, and they can reconstruct the whole thing because they know the physics. So if they see it in a little part, it automatically goes to everything else. So probably at some point we can play tricks and tell it like, okay, you have this field, but here's a hole in it. Fill it in just using the physics, and it would probably do pretty darn well.
Matthias, then you.
So mentioned you only have these intensity images at a fairly low cadence, but what's the cadence at which you enforce the physics during the?
Well, unfortunately, right now that's about the same. I was hoping that, we don't know what the right thing is. And obviously this is one of the, things one can do is just to increase that and see how it gets, particularly this, I think this image interpolation is pretty neat.
I was wondering,
Yep.
why is it not working better if it has the physics?
Probably because I'm not enforcing the physics.
Because
frequently.
I mean, when you showed the example, I think of the linear
Yep.
damped oscillator, you had the physics frequency indicated on there,
Yep,
and that
yep,
was much
exactly.
higher
Yep,
than the
yep.
data points you had. So I was
Absolutely,
wondering
you
if
have
we
to,
do something
yeah.
similar here.
I should, yes, I should, yep. At some point, the thing is, you hit the limits even of a laptop. I haven't tried it with my new one yet. But at some point, once you have to swap out the disk, even with a fast SSD, it starts to become problematic. So most of these things, I'm actually not even compute limited, but it's the physics is still relatively simple for it to calculate. So it's mostly bringing in the data that is often an issue. And the data can be as simple as X, Y, Z, T coordinates. Once you have hundreds of millions of those points, maybe there's a clever way to generate those instead of taking them out of an existing tensor. So, and all I can tell you is that when I worked on this, there were many, many times where I got things to suddenly go a factor of 10 faster. they're recognizing how you have to do things, that you can reshuffle the data, you structure it differently in your memory, and suddenly you get a factor of 2 acceleration easily, sometimes a factor of 10. So there's a lot of it's with like all this AI stuff. Sometimes people would better spend time to think about it, and you wouldn't need these huge compute capacities. It's easy to just throw pure compute power at it, but often I find that actually thinking deeply about this can make a huge difference.
Johan?
So the evolution's, mostly the evolution controlled by the physics, the constraint of the physics, minimizing the difference to the physics. So then why the solution will drift when if you stop enforcing observed constraint, then the evolution drift? Is that because of similar to this, butterfly effect, that you have more alternate universe and you have to find the one? It's like
No.
simulation?
I think, there are many components that could come in. One is what Matthias mentioned, is that the physics simply has to be enforced more frequently. If you don't do it frequently enough, then, it's just too much, right? It's like, I don't know, for an explicit code, you have to step fairly frequently, right? And for an implicit code, you don't have to time step as frequently, but I can say that without really understanding it. And this applies to this too. I have not the faintest idea. Is this now an implicit or an explicit code or something in between? So what is it? This Kura-Hilbert?
CFR, yeah.
Or
Kura, maybe free
yes.
condition. For the explicit code, I don't know what was the grid spacing of that, or kind of the original B?
That's the original Bifrost. So
it's like the fractions of a second time step in there.
Yeah. So I don't know. We'll figure it out.
It's kind of tricky because your physics from neural network doesn't really have a grid spacing, since it's an
it does not.
So it's not clear what that concept
exactly.
is.
Yeah, exactly. So tons of PhD theses.
Other questions? And anyone from online? Okay, if not, let's thank our speaker again for an excellent lecture.